So let me start by some very general nonsense. If you want to study some mathematical object, one thing you can do is try to decompose it into pieces which hopefully will be simpler, and then you can try to understand your object by understanding the pieces and how they fit together. And if you're interested in a group G, you can try to decompose it as a graph of groups, or just say as an amalgam, right? G equals A star B over C, and you hope that A and B will be simpler. And then A and B may themselves be amalgams, so you can decompose A, and you get new groups, and you can decompose these new groups, and then the question that arises, of course, is whether this process is going to terminate. We had an example yesterday in Zlier's talk about this. Okay, and so in this, there's an analogy, and which is also a strong source of inspiration coming from low-dimensional topology, and especially the topology of three-manifolds. So if you want to study a three-manifold, you can cut it along spheres and tori, and you get what's known now as the Jsj decomposition. And the letters Jsj refer to Jacob and Shalen and Johansson, who introduced this, I guess, in the late 70s. And of course, now we know, thanks to Thurston and Perelman and other people, that the pieces of the Jsj decomposition have nice geometric structures. And this theory of Jsj decompositions has been carried over very successfully to group theory. And there are many names here, like Rips and Sella and Dunwoody, Sergeyev, Fujiwara, Papazoglu. There are many names here. So that's one thing you can do. And going back to three manifolds, you can also try to cut your three manifold along more general incompressible surfaces until you end up with a disjoint union of balls. And the word here is called hierarchy. And no. Okay, and if you have a manifold that has a hierarchy, a Haken manifold, then you can use this to prove results about your manifold. Okay, and this has also been carried over to some extent to group theory. Okay, so if we forget about three manifolds and we go back to groups, we have a group, we start decomposing it, we have some process, and we want to know that this process is going to terminate. And usually you're going to get termination from what's known as accessibility results. And these are results that basically give you some control about how complicated things can get when you start decomposing your group. And here also there are many names like Linnell, Dunwoody, Bestvina, Fein, Sella, Weidman, and also Delzan, Potiagailo, and Lauder, Twican. So there are lots of accessibility results. And what I want to talk about today is some variation on this theme, which we'll call vertex finiteness. So let me explain what we mean by this. Okay, so we have a group G which is going to be finitely generated. And we can consider all splittings of this group, all splittings of G. And when I say splitting, you may understand either a general decomposition of the group as a phenomenal group of a graph of groups, or much more simply, writing G as an amalgam. G is A star B over C, or an HNN extension, G equals A, C. So I'm confused. I don't know how to write HNN anymore after Laurent Bartholdi's talk, but I'll just stick to HNN extension, and I will represent this graphically as usual as here an edge where A and B are vertex groups and C is the edge group, and you obtain G from A and B by amalgamating along C, and here the picture is the following. So A and B are going to be the vertex groups, and C is going to be the edge group. And you could, of course, also think that your group is acting on a tree, and A and B are going to be stabilizers of vertices, and C is going to be the stabilizer of an edge. OK. And we want to have some control over what's going on. And in order to hope to have some control, it's well known that you need to place restrictions on the edge groups, on the group C. Geometrically, you want to cut along something which is not too complicated. So you want to restrict what you're going to take as your group C. And so I'm going to fix a family of subgroups. So fix A, a family of subgroups of G. And we're going to require that the edge groups belong to this family. So to fix ideas, just think that C is a family of cyclic subgroups. OK. So now I can give the definition. So we want to look at all splittings with edge groups in this family C. So just think A star B over C, where C is in this family, say a cyclic group. And presumably there may be infinitely many different splittings of my group. So I want to look at the edge groups that appear in the, I want to look at the vertex groups. The edge groups are all going to be, say, cyclic, but I want to look at the vertex groups, all vertex groups that appear in my splitting, and I want to know whether I'm going to see infinitely many different groups up to isomorphism, or whether I'm going to see the same groups over and over. Okay? So the question is going to be, am I going to get infinitely many non-isomorphic vertex groups or not? So let me write this as a formal definition. So I say that G satisfies vertex finiteness over A, and I will abbreviate vertex finiteness usually by VF. So there is vertex finiteness if up to isomorphism only finitely many groups occur as vertex groups, of splittings of G over groups in A. I will say over A over groups in A. Okay, so is this clear? This is a key definition in this talk. So is the definition clear? I'm looking at all the ways of writing G as, say, A star B over C, where C is in my family. And I look at all possible groups, A and B, that I see. And do I see infinitely many different groups or not? OK? Is this clear? All right. So let me tell you briefly why we got interested in this definition and this notion. We were working on automorphisms of relatively hyperbolic groups. We wanted to prove certain results concerning fixed subgroups or certain subgroups out of G, for G a relatively hyperbolic group. For instance, subgroups fixing a certain set of conjugacy classes of elements of G, what we call McCool groups, or groups of automorphisms preserving some action of G on an R tree, for instance, a tree in the boundary of Köhler-Wogman's outer space, and we needed some vertex finiteness statements. So I'm not going to talk about these applications to automorphism because I would need to introduce too much stuff. I will just focus on this vertex finiteness question. Okay, and what I want to do is give you some examples and counterexamples and theorems. And if I have time at the end of the talk, I will say a few words about another finiteness property having to do with finite extensions. But let's just concentrate on this vertex finiteness. So tableau 2, tableau 1. All right, so examples and counterexamples. Okay, so the first type of examples are going to be free splittings, meaning that my family A is just going to consist of the trivial group. So this is a free splitting, meaning that I'm just interested basically in writing G as a free product A star B. And in this case, it's well known, it follows from Grushko's theorem, that A and B, they are free factors, and there are only finitely many isomorphism types of free factors in a given finitely generated group. So in this case, Grushko's theorem implies VF. By VF, I mean I have vertex finiteness for my given group G over A, which in this case is just the trivial group. Okay, so this is fine. And since this is a conference about asymptotic properties of groups, let me ask an asymptotic question. So take a group and take a descending chain of finite index subgroups. So the Gn, a descending chain of finite index subgroup. And if you want things that G is residually finite, so the intersection of the Gn's, you want to be just the identity, just the trivial group. Okay. And then you can define f of Gn as the number of isomorphism classes of free factors of Gn. So either that or something similar. It's not clear whether this is the right definition, but something in this direction. And then you can ask how this number grows with respect to the index of Gn. So the question would be, how does f of Gn grow in terms of the index of Gn of G? Okay, just a question. All right. So this was example 1, free splittings. Okay, example 2, splittings over finite groups. So here A is just a family of finite subgroups. Okay, so I want to look basically at A star, writing G as A star B over F with F finite. Okay, and there's a proposition saying that in this case, vertex finiteness holds if the order of F is bounded. So if you look at splittings of your group over subgroups finite subgroups of order less than 1 million, you're only going to see finitely many vertex groups. And this follows from Linnell's successibility result. On the other hand, if you don't bound the order of F, you don't have vertex finiteness in general. And there's a very easy trick to see this. Take a group G, which is a free product H star Z. So now the trick is the following. If you have a subgroup C contained in H, you can rewrite this as H, the product of H with C star Z amalgamated over C. I've just added C to my group, but the amalgam identifies it with the C that I already had inside of H. And so here I get C star Z as a vertex group of a splitting over C. And from this you can see that vertex finiteness holds if and only if there is a bound for the order of finite subgroups. Finite subgroups of H. So that's another fairly simple example. Okay? All right, so I've told you about free splittings, splittings over finite groups. Now I want to talk about splittings over cyclic groups. So, maybe I will leave the definition on the board. So 3 cyclic splittings. So I'm interested in the case when C is just Z. And I could also do virtually cyclic splittings, but I will stick to cyclic splittings. OK, so a simple example for free groups, there is finiteness. And that's easy because if you take a free group Fn and you write it as A star B over Z, then the rank of A and B is at most n. The rank of A, B is at most n. So you only see finitely many groups up to isomorphism. This is a very simple example. Another example is surface groups. So suppose your group is a phenomenal group of some surface. So we are looking at cyclic splittings of the surface group. And it's a standard fact that cyclic splittings of a surface group comes from curve on surfaces. Cyclic splittings of pi1 of sigma are dual to curves on the surface sigma. So for instance, if I draw this curve here, I get a free product with amalgamation over the cyclic group carried by this curve. And if the curve is non-separating, I get an H&N extension. And every cyclic splitting of the surface is obtained in this way with several curves if I have a more complicated splitting. And so the vertex groups are just phenomenal groups of subsurfaces. Vertex groups are pi1 of subsurfaces. And so they are free groups and their rank is bounded. So there is vertex finiteness here. OK, but in fact we have much more in this case. Because the subsurfaces have bounded topology, But it's also true that splittings comes from curves, and the set of curves in a surface is finite under the action of the mapping class group. Right? There are only finitely many orbits for the action of the mapping class group on simple closed curves on the surface. So what this means is that in this case, we have something much stronger because we only have finitely many splittings up to the action of the mapping class group, which is the automorphism group of the surface group. So this is a special case of a more general result, which is due to Sella and Derzan. Which is the following. So G is a one-ended hyperbolic group. So hyperbolic meaning Gromov hyperbolic. So G is a one-ended hyperbolic group up to isomorph. No, sorry. There are only finitely many cyclic splittings of G so splittings of G over a cyclic group up to the action of out of G. So I have a finite set of splittings, and every splitting is obtained by composing that splitting with an automorphism of the group. Okay, and this result may be generalized. So with Vincent, this extends to relatively hyperbolic groups, to G hyperbolic relative to polycyclic subgroups. So this is an extension, but the one-endedness condition is really essential. Okay. So still thinking about cyclic splittings, I've given you two simple examples where there is vertex finiteness. Now I want to give you an example where there is no vertex finiteness. So this goes up, this goes down. Okay, so I'm still in three splittings over cyclic groups, and now should be C. There is no vertex finiteness for the following group. So G is going to be an amalgam of F2, which is a free group of rank 2, which I will think of as the free group on X and Y, and I will amalgamate it with a solvable Baumschlag solitar group BS12. So this is a group generated by two elements T and A, and T conjugates A with A square. And I have to tell you what the amalgamation is. So it's an amalgam over Z. And the amalgamation is going to identify the commutator xy with the element A. So this is a group which is hyperbolic relative to a solvable group. It's one-ended. And I'm going to show you that there's no vertex finiteness for this group. OK, and that's also very easy. I'm just basically going to do a change of variables. So I'm going to replace x and y by their conjugate by t to the n. So xn is going to be tn x t minus n, and yn is going to be tn y t minus n. So I'm going to replace my generators x and y by xn, yn. So if I do this, I'm going to rewrite G as the free group generated by xn, yn. And let's see. And I'm going to amalgamate it with the same Bumps-like solitar group. But what is the relation? So now the relation here was xy equals a. The relation now is going to be that the commutator of xn yn. What is the commutator of xn yn? Is just tn a t minus n, right? Because the commutator of xy is a, and this is a to the 2 to the n. So the relation now is this one. So this is a new presentation of the same group. And I can rewrite this as an amalgam of the group generated by xn, yn, and a with BS12, the amalgam being over the group generated by a. And the relation that I have here is simply that the commutator of xn, yn is a to the 2 to the n. So I'm going to give you another way of looking at this manipulation. But the point here is that I have infinitely many splittings here, and I have vertex groups here which depend on n, and these vertex groups are non-isomorphic when n varies. So here I get infinitely many groups. So I don't have vertex finiteness. Okay, there's another way, a more graphical way of understanding this. So my original splitting was F2 BS12, and here the edge group was A. And what I'm doing really is just replacing the inclusion inside BS12, composing it with an inner automorphism of BS12. And can also view it with another picture, writing BS12 as an HNN extension, with here I only keep a cyclic group generated by A, and here I have a cyclic group, and I have two inclusions of the cyclic group inside the group generated by A, and on one side it's the identity, and on the other side it's multiplication by 2. And if you know about sliding in graph of groups, what I'm doing is taking this edge and sliding it n times around this loop. That's another way of doing the same manipulation. Okay, so I don't have vertex finiteness here. And if you think about what I've been doing in this example, what makes this example work is the fact that in BS12, the cyclic group A is properly contained in a conjugate of itself. So it's properly contained, or properly contains, it's the same thing, properly contained in a conjugate. And this is what makes this example work. And this is possible in a solvable group such as BS12, but it wouldn't be possible in a polycyclic group, because in a polycyclic group, every subgroup is finitely generated. So this would be impossible in a polycyclic group. And what's really relevant here, the property of polycyclic groups that is really relevant for us is what I call an index gap in polycyclic groups. So that's the following statement. Suppose you have a polycyclic group and a subgroup. So I have A, how should I call it, A or C? Well, it doesn't matter. So suppose I have A contained in H, and H is polycyclic. So given A and H, there is a constant, a positive constant M, such that if I take any group, any subgroup containing A, so if I have A, if I have a group B that contains A, and I look at the index of A in B, this is either going to be infinite or bounded. So the index of A in B is bounded by my constant M or is infinite. So given A, you cannot have subgroups containing A with too large a finite index. This is a property of cyclic groups, and it's also true for polycyclic groups. And this is, in this context, this is the difference between solvable groups and polycyclic groups. So now I can state a theorem. I want you down. Okay, so theorem, I'm still in cyclic splittings. So theorem, this is by Vincent and I. Vertex finiteness holds for cyclic splittings or for virtually cyclic splittings, splittings over virtually cyclic groups. Of G if G is hyperbolic, relative to polycyclic or virtually polycyclic subgroups. So this is okay when the parabolic subgroups are polycyclic, but not when they are solvable, as the example shows. So I'm not going to prove the theorem. One of the key ingredients in the theorem is this Jsj decomposition that I mentioned earlier. Somehow if you take an arbitrary splitting of your group, you're going to somehow compare it to the Jsj splitting and see where the vertex groups come from and realize that up to isomorphism you can only have finitely many. And this index gap, which is somewhere here, is another ingredient in the argument. Okay, so this is cyclic splittings. Now I want to talk about abelian splittings, so splittings over abelian groups. And here we saw that the difference was between polycyclic and solvable, and now the difference is going to be between abelian and nilpotent. So, no. And if the group is one-ended, there's a stronger result that there are only finitely many splittings. But if you only want control over the vertex groups, you can allow your group to be infinitely ended. Okay, so this is 4 abelian splittings. So these are splittings where the edge groups now are going to be abelian subgroups. Okay, so let me first show you a non-counter example. Okay, suppose we want to find an example of infiniteness. So here's one thing we can do. We can look at an amalgam G1 ZP, where C is going to be some subgroup of ZP, so an abelian group. And G1 is your favorite group. And suppose I have a group P, which is between a subgroup of ZP which contains C. So then I can do the same trick. I can rewrite G as G1 amalgamation with P over C, and then amalgamation with ZP over P, and I get here a new vertex group. And the picture is I have G1, I have C, here I have P, P, and C, and ZP. And I can try to prove infiniteness this way, because presumably there may be infinitely many different groups P. But it's easy to check that this doesn't work. So if I look at this new vertex group GP, which is G1 amalgamated with P over C, I have only finitely many. I have finitely many GP up to isomorphism as P varies. And this is easy to see. Let me just give you an example. Suppose ZP is generated by A and B, and C is generated to A to the 6, and say P is, let's say, A square Bn, where n is an integer, then my group GP is just G1 amalgamated over A6 with A square Bn, and of course this group GP doesn't care what n is, right? So even though I have infinitely many n's, I only have one group up to isomorphism. So this is not a way of getting infiniteness. And a similar example, which I'm going to do because it's relevant to what's going to come next, is I could look at G1 ZP G2 and replacing it by G1 P G2 and ZP. This is just the same example whenever P is a group containing both the edge groups C1 and C2, but similarly I'm not going to get anything interesting in this way. So this doesn't work because ZP is abelian. What I'm going to show you now is I'm going to get infiniteness if I replace ZP by a nilpotent group, the Heisenberg group. So this was a non-counter example. Now let me give you a real counter example. Okay, I have 7 minutes to give you this example. So be a real counterexample. By counterexample, I mean an example where there is infiniteness. So I'm going to replace ZP by the Heisenberg group. And I'm going to view H as a group with presentation A, B, T, and relations AB equals BA, TAT inverse equals AB, and TBT inverse equals B. Now, if you look at this presentation, you see that B is a commutator of A inverse and T, and it is central. So this is indeed the Heisenberg group. And I want to present it this way to view it as a mapping torus of the matrix, a unipotent matrix acting on Z square. This is what this presentation tells you, that H is a mapping torus. OK, now what is the group that I'm going to look at? I'm going to do an amalgam this way. Here I'm going to have a group G1. Here I'm going to have a group G2. Here I'm going to have the Heisenberg group. And in the Heisenberg group, I have this element A. And I'm going to take an element A1 in G1 of infinite order and an element A2 here. And the amalgam will identify A1 and A2 with the element A in the Heisenberg group. So let me just make room to draw diagrams. So the first diagram is, here I have G1, I have H, I have G2, and H is generated by A, B, and T, and here I have A1, A2, and the presentation is that G is generated by G1, H, G2, and the relations are A1 equals A, A2 equals A. Okay, this is my group. Now there's another way of viewing this group when I recall that H is this mapping torus, which is nothing but an HNN extension. So I can draw the following graph of groups, where here I have G1, G2. Here I have the group generated by A and B, which is just a Z square. And here the edge group is Z2, and the inclusions here are the identity, and here my unipotent matrix. This is another representation of the group. OK. So this is an HNN extension of the group K0, which is generated by G1, G2, A, and B. And the relations are AB equals BA, A1 equals A, and A2 equals A. So K0 is just the phenomenal group of this horizontal graph of groups here. OK. And now what I'm going to do is I'm going to take this edge here, the edge on the right-hand side, and I'm going to slide it around the loop n times. So this is what I'm going to do geometrically. And algebraically, I'm going to replace G2 by T to the n, G2, T to the minus n. And what's going to change is my relation. So the relation A2 equals A becomes, just like in the example with BS12 that I gave you earlier, it becomes A2 equals 2 to the n, A to the minus T to the minus n, which is just A B sub n. So what happens is these graphs of groups are going to change a little bit. So how are they going to change? So here the edge group was A, and now it becomes A B to the n. So I'm using the orange to show you what changes with n. So what changes here is this. And similarly here, the edge group was A, and now it becomes A B to the n. This is what changes in these pictures. And in the presentations, what changes is that the relation now is A B to the n. And similarly here, it's A B to the n. So in this way, I have infinitely many splittings of the group. And another thing that changes is this group, because this group is different. It's now a group K sub n. And the whole point is that presumably K sub n depends on n. Because if you look at what happens near this vertex group here, which is a Z square, if you look at the subgroup generated by the edge groups, here you have A, and here you have A B to the n. So the subgroup generated by the edge groups has index n in this group here. So all these splittings are going to be different. So presumably my groups Kn change when I change n. So that's presumably. And of course, to make this really happen, I need to choose G1 and G2 correctly. This can be done. So if G1 and G2 are well chosen, all groups Kn are different up to isomorphism, so there is no vertex finiteness. So I'm just going to take 30 seconds to state the theorem. So the theorem, which is also with Vincent, and that's easy, I don't have to erase everything. So VF holds for abelian splittings of G is hyperbolic relative to abelian subgroups. And here, I couldn't have parabolic subgroups being nilpotent, but abelians are fine. So this applies, for instance, to limit groups or groups acting freely on R entries. And my time is up, so thank you for your attention.
Are there any questions?
I'm sorry?
Can you make that
virtually
abelian splittings?
we don't know whether we can put virtual. Yeah, virtually is somehow different. We don't know exactly what happens with virtually.
Any other questions? Wait.
Where does hyperbolicity come up?
Yes. Where do you need hyperbolicity in such results?
Because we need to understand the Jsj. So that's why we need the hyperbolicity.
Anyone else?
Have you looked at weakenings of VF, say not up to isomorphism, but up to commensurability, or?
No. Up to commensurability, I don't know.
So many of your examples seems to work only.
Yeah, that's a good idea. We haven't done that, but that's a good idea. So I don't know. Did you think in these examples the groups are commensurable? Okay. Anyway, it's a good question.
Anyone else? No? Okay, let us thank the speaker again.